Hello, everybody. Hey, this is our actually going to be our second lecture of the week. The first one is online, and there'll be some other ones, but this is on Tuesday, fourth period, and so there's a couple of your classmates out there listening, which is why I have my mask on. And they might be asking questions, and I'll probably be asking questions to them. So if I'm not in the frame, then you guys just know I'm right here and go from there. So I will have some questions on this in an assignment, and you're going to take notes like the other videos that you're watching this week. All right, so our first lecture is going to be on one-dimensional kinematics. So what do you suppose, or do you know, kinematics? What does kinetic mean? Movement. That, Tyler, is perfect. Okay, kinetic from kinesos, from the Greek, means movement. Okay, so this is essentially measuring movement. So we are going to do this one-dimensionally, and then next week, which is essentially going to be chapter 3, we're going to be doing 2 dimensions. So chapter 2 is one-dimensional kinematics. And when I say measuring movement, what might do you think that we're going to talk about? How do you measure movement?
Like the distance it goes.
Distance. What else? Can you have a distance without movement? Velocity. Okay. So distance, velocity. Okay. And I'm going to say /speed, velocity /speed. Is there a difference? Is there a difference between speed and velocity? Yeah. There is most definitely a difference between speed and velocity, except for this chapter 2 unit. Okay, so this right here is going to be the same for chapter 2. Okay, and that has to do with scalars and vectors. Scalars and vectors. Okay, so speed is a scalar. And you guys are going to watch and answer some questions on the difference between a scalar and vector. That's going to be a separate assignment. You're going to essentially watch a voiceover of a slide presentation. Pretty straightforward. Mr. Calicott from another class is going to, I'm going to use his, okay? And then we have velocity, which is a vector. Okay, so here's the difference between a scalar and a vector. Okay, they are both quantitative observations. And if you have not seen, you will see in lecture number 1, the two types of observations, qualitative and quantitative. And in a quantitative observation, you're going to have a number and you're going to have a unit. And there are 2 types of measurements. There's going to be scalar, which is going to have a number, a unit, and a vector, which is going to have a number, a unit, and a direction. Okay, for example, if I am going to say that direction right there is positive, okay, and I start here and I'm just kind of walking along like this, I'm going to have a certain speed. Let's say it is 1.5 meters per second. 1.5 meters per second. As long as I'm going the same direction and in one dimension, okay, the speed and velocity are going to be the same thing. Okay, and I will elaborate when we get to some of these formulas, when they would be, what's the difference, and I'll kind of reiterate that, even though for this first section, they're going to be the same, just to make it a little less confusing. Now, if I say that this direction is positive and I'm just kind of cruising along like this, right, then I am going in a negative, I'm going to have a negative displacement. I'm going to have a negative displacement, but I can't have a negative distance. I can have a negative displacement, but not a negative distance. All right, so let's take a look at what the equation for that would be. And we're going to say velocity, okay? And we're going to put speed here, okay? Now, there's really not a universal symbol for speed. So usually, because of that they're synonymous, as long as they're going in the same direction, we usually kind of use the same symbol. Okay, but that is going to be distance divided by time. That is probably nothing new. That is probably nothing new. But I am going to say just a regular, so we're going to kind of cross that out in purple, and now we're going to say displacement over time. And displacement over time is going to be velocity. Okay, displacement over time is velocity. Distance over time is speed. Okay, but again, they look similar because as long as you're going in the same direction and in only one direction, then they're going to be the same. Okay, so we're going to say distance is the length of the path taken. Okay, so if we start here, okay, the distance is going to be the length of the entire path. Okay, now the displacement is equal to the position final minus the position initial. Okay, so if we are talking about this same line here, okay, this would be my position initial, and this right here is my position final, okay, then my displacement is going to be there. So it's essentially, it is a straight line. It is a straight line, and it is going to be the difference from where we start, or sorry, it's the difference between where we end and where we start. Okay, and again, if we look at here, if in this distance we were going in the same direction, okay, on the same path, then distance and displacement would be the same. And that's why in the beginning here, they are going to be the same. All right. So I'm going to make this a little more abbreviated, and I'm going to say distance is equal to the length over, it's just the length, right? And I'm going to say D is equal to position final minus position initial. Okay, so how do you know if it's distance and how do you know if it's displacement? You are going to essentially get that from the context clues of the question, all right? But again, for right now, these are going to be the same, all right? And for the most part, once we get deep into this, we're going to be talking about displacement. we're going to talk about displacement, okay, versus distance, okay? All right. So let's talk about the equation. Let's talk about the equation for speed and velocity, and we're going to say it's going to be distance over time. If I say it's distance over time, then I'm really talking about velocity, right? Speed, because it doesn't matter the direction. Okay, now if I'm talking about velocity, it's going to be displacement over time. Again, first time, it is going to be the same. So in the beginning, it's going to be the same, but for now, it is going to be, later, we're going to have a distinction. But you guys are going to be sophisticated enough to distinguish that fairly easily, okay? But in the beginning. All right, so, and notice here that I said x final minus x initial. So you, okay, are a little more used to having a Cartesian plane, where you have x and y, okay? Now, if you had, you might also see an r here, okay? So you could have y final minus y initial. You could have r final minus r initial, okay? So as long as you're going in one dimension, let's say in the x dimension, which we're going to do in the beginning here, then it's not really going to matter, okay, because we're in the x direction. But we could also do that in the y direction, which we will talk about later in this chapter 2 when we talk about gravity, and we might see why. But it could be any direction, right? So if you went here, you started at 0, and you went to, let's say, 4, okay, and you went 3 in the y. If you went 4 in the x and 3 in the y, then what would your change in r be? If you went change 4 in the x and you went the change in 3 in the y, then what would your change in r be? It would be 5. So you guys recognize that as a Pythagorean triple, okay, a 3, 4, 5 triangle, okay? The other common 3, 4, 5 triangle is a 5, 12, 13, triangle, in which 5 squared plus 12 squared is equal to 13 squared. And that is another common Pythagorean triple that's low. And in your future, you're going to take a lot of math diagnostic tests, or even in the SAT, or in college when you're doing math and physics courses, or even other science courses, or post that GREs, MCATs, LSATs, all sorts of things. When they're giving you math problems, they really would expect you to know what a 3, 4, 5 triangle is, okay? And so I'll use that a lot, probably a little bit less so of a 5, 12, 13, but those you should really know what they are, okay? And I'll use them a lot for examples, because then I can do the math in my head really quickly. Okay, so I'm going to kind of make a important distinction, particularly in light of your question of the day. So you will find in your week 1 material, there is a question of the day that is going to be asking about average speed, okay? And that question for average speed, that bar over that line means average, okay? And I'm going to put a little speed here to indicate that it is in fact average speed and not average velocity. And we're going to say that that is total distance divided by total time. All right. Now, and at the end of this period, when I'm kind of done with this lecture, I'm going to give you an example that is simpler but similar to your question of the day. Okay, and average speed is going to be the distance over time, total distance over total time. Okay, so that is an important distinction. All right, so let's talk about this a little bit more here. So we're gonna kind of set up a graph here, okay? And along the horizontal axis, we're gonna say that this is equal to time, okay? And our units are in seconds, and we're going to say distance slash displacement, okay? And our units are going to be in meters, all right? So we're just graphing that. And again, for now, they are going to be synonymous, distance and displacement, okay? All right, so let's say that we have something like 1, 2, 3 meters, and let's say we have something like 1 second and 2 seconds. We can get out here 3 seconds. And if we have a graph, that looks like that, okay, what is that indicating? What does that graph indicating as far as measuring movement? What does that graph tell you? It's one-dimensional. Okay, what else? How fast is that line on that graph indicating? What's that?
1 meter per second.
It is not 1 meter per second. It's not changing its speed, okay? So what that's saying is it's going 0 meters per second. But where is it going 0 meters per second? At the 3 meter position, at the 3 meter mark, okay, it's going 0. So if we had a line that was there, okay, that would also not be moving, but it would be at 2. Okay, and if we had this, it would not be moving at 1. If we had a line down here where it was -1, this would be not moving at -1. Now, as soon as we go into this negative, okay, we are no longer in the distance, but only in displacement, okay? You cannot have a negative distance. You cannot have a negative distance. For example, if I'm starting here at 0, okay, and I go backwards 1 spot, okay, I've still gone a distance of 1, right? If I'm back here at 0 and I go, we'll call it forward 1 meter, I still gone a distance of 1, okay? We cannot have a negative distance. But on the other hand, okay, if I'm starting here at 0 and I go backwards 1 spot, now my displacement now can be negative. In the same way, I start out at 0 and I go this direction, now my position is 1, okay? So in the first case, when we're talking about distance, my distance was 1 both times. We can kind of think of it as absolute value, okay? Now, in the first case, when we're talking about velocity, okay, or displacement, my displacement is my final position, which is -1 minus 0, which would be -1. So my displacement would have gone negative. And in the last case here, my final position is 1, my initial position was 0, and therefore I'm going to say 1 minus 0, and therefore my displacement would have been +1. So we can have a positive or negative displacement, but not a positive or negative distance, which means that we cannot have a negative speed, only a positive speed, And we can have a negative velocity as well as a positive velocity. Yes, sir.
Okay.
Okay, gotcha. All right. So we are good. We are good there. Now let's take it to something that is going to be a little more common in our studying of physics. Now let's say that we had a line like that. Okay, we had a line like that. What does that line represent? What does that line represent? Is an object moving?
Yes.
And what is its speed or velocity?
1 meter per second.
I think it is going to be more than that, but I think you're on the right track. And the reason I believe you're probably saying 1 meter per second is because this looks like it is at a 45 degree, which means you'd go up 1 over 1. Okay, but we have to look at our scales there, and we can see it's going up 3 over 2.
Okay,
Yeah, and again, common mistake, but because normally, particularly in math, you're going to have each of the axes, x and y, are going to be proportional usually, but not necessarily on another graph here. So now we are going to say, okay, we're going to have a change in 2, okay? So we're going to have a change of 2, and here we're going to have a change of 3, and this would be 3 meters, and this would be 2 seconds. All right. Do you guys know what letter that is? What letter is that? Delta is correct. Well done. Now, technically, that is capital delta, okay? And universally in math and science, okay, this means change. Okay? Now, do you guys know what letter that is? Say delta. Okay, you guys, that is delta 2. This is capital delta, and this is lowercase delta. Were you guys in Medine's calculus class first quarter?
Yes.
Were you?
Yeah.
Okay, so you're probably going to recognize this more as something like dt. Okay, now it really, okay, it should really be little delta t. Okay, but because this is really a lot more common on a keyboard, okay, this has essentially dominated here, but it really means also means change. But this means a big change. This means a macroscopic change where this little delta, or dt in this case, very common for science, that is a very small change. That is an infinitesimally small change in time, which is what we have in a differential in calculus. Now, if you guys are not in calculus, then you're still going to be fine, because even though I'm going to be teaching this with calculus in mind, it is not going to be as intense from a calculus point of view than anything else. So if you have not taken calculus, you will be able to learn the calculus part that you need. Okay, so it is in the beginning, and you might have had part of that in your pre-cal class that you might be in or already taken. If not, again, I will catch you up if you haven't had that. Okay, so I'm going to get rid of this for right now so we have a little more room. Now, you guys, what we have here is the rise over the run. And so I'm sure from your math you will calculate that that is the slope. Okay, and you might recognize that as delta x over delta y. Delta x over delta y as your rise over run. That is the slope. Okay, but in this case, we do not have change in x over change in y. What we have is change in x over change in time. Change in x over the change in time. And if we go here, we're going to have this velocity here as displacement over time. Well, if we take the displacement in the x direction, we really just have delta x over delta y, which is going to be equal to our velocity, Okay? Now, and let me give us a little more room over here. If we say y is equal to mx plus b, y is equal to mx plus b, then according to this graph right here, what is our m? What is our m? It is our velocity, but what is the actual numerical value for that?
3/2.
3/2. Now, in science, I do not want fractions. I want decimals. Okay, so 3/2 is obviously going to be 1.5. Okay, so for our example, that's going to be 1.5 x. What is our b? What is our b here?
0.
It's going to be 0 because it is going to have the y-intercept at 0. Okay, so that is going to be plus 0, and this is going to be y. Except remember, this is the x is our independent variable. The x is our independent variable. So we're going to rewrite that as 1.5t, 1.5t plus 0. And that, remember, x is our independent variable in this case, okay, because it's going, the vertical is really our independent variable. We get so ingrained as x always meaning horizontal and y always meaning vertical, okay, that when we change axes, okay, that sometimes it's sort of confusing. So most of the time in physics, our independent variable is going to be t for time, and our dependent variable is going to be something else. Very often in math, you are looking at the relationship between positions horizontally and vertically. Okay, so these essentially become interchangeable. Now, if we want to get this 1.5 all by itself, we're going to divide both sides by t, okay, and then our x over t, okay, is going to be 1.5. But what are our units? What are our units for x? What are the units? That's going to be meters. And then our units for time are going to be seconds. So essentially, we can say that our velocity, which is x over t, technically speaking, it's change in x over change in t, okay? And so that's going to be 1.5 meters per second. Does that make sense? Okay, so we can see that the slope of that line of a position versus time graph is going to give us our velocity. The slope of a position versus time graph is going to give us our velocity. The slope of a distance versus time graph is going to give us speed. The slope of a distance versus time is going to give us our speed. All right, you guys ready to change things up just a little bit? Okay, same graph, okay? And what I am going to do is I'm going to kind of redraw this so we don't have so much stuff, and then we can kind of prefer that. And all right, so essentially we've got the same graph here. Okay, so this is going to be, now I'm going to reserve this to be displacement. That's going to be meters. And we can even call that X, okay, because we're going to measure this displacement in X. Again, it could be Y, it could be R, okay, it doesn't really matter. But because we're doing one-dimensional right now, we're going to kind of think of our one dimension as being X. Think of it as horizontal. And then our time here is going to be in seconds. So oftentimes, you're just going to see, to make it quick, you're going to have a position versus time graph. Okay, so let's get this same 1, 2, 3, 1, 2, 3, 1, 2, 3. And if we start here and we end here, this is 1 and 2. Okay, and so we know that in a straight line, let's see, just long enough. Okay. That right there is essentially the same line. But, okay, now we have a dotted line there. But what if we did something like this? All right. Now, in this first second, now remember, we already know that this line right here, 1.5 meters per second, is that line right there, that dotted line indicating 1.5 meters per second. So right here, at this position right here, that might be, let's say, 0.4 seconds. What would you say that the velocity is? And I'm just going to ask you, is it faster or slower than 1.5 meters per second?
Slow.
Why?
Because it's moving less.
Well, okay. And the way to indicate that is if we take a look at the slope, okay? Now the slope is going to be the line that is tangent to this curve or this line, okay? Now, you guys probably remember from geometry that if we have a circle and we have a line that is touching it at one point, that line is tangent to the circle. Does that ring a bell? You might remember, for example, there's some postulate that says if you have a line that is tangent to the circle, then the radius is perpendicular to the tangent line, that sort of stuff. All right, lots of stuff there. Now, if we have this curve or this line, at any point right here, if we put a sloperometer, and this right here is a sloperometer, and we put it like this, and now we draw that line, okay? And now we have the slope of that line, okay? Now we can do the rise over run, okay? And that rise over run could be a smaller triangle or a bigger triangle. It doesn't really matter. But if we have a more precise graph here, we could determine pretty closely what the actual velocity would be here at 0.4 seconds. Okay. Now, if we take a look at this particular point up here, which would be at about 1 second, okay, now we look at the slope of this line. Is it going faster than 1.5 or slower than 1.5? Why? Because the slope is now greater. The slope is now greater. And if we were to do a slope of this tangent line, we would see there'd be a greater rise over run, and therefore this would indicate a velocity that would be greater than 1.5, and here this velocity would be less than 1.5. So you can determine what the velocity of an object is that is graphed on a position versus time graph based on the slope, okay? And you, in the future, will do that exact thing, okay? And if you know the equation, if you know the equation of that line, okay, how can you determine the tangent? How can you determine if you know that right there has, for example, x is equal to 3t cubed minus 4t squared plus 5t minus 6. Okay. How could you determine the tangent line to this equation? You take the derivative, okay? And the derivative of this, which would be dx dt, okay, from a calculus point of view. Again, non-calculus people, you're going to be fine here, and you will learn this. But if we're going to take this differential, this would be 9t squared minus 8t plus 5, okay? And if we put in 1, okay, then we would have 9 times 1 squared would be 9 minus 1 plus 5, okay? 9 minus 8 plus 5 would be 6, okay? Now, I just made this up, so it does not correspond to this, okay? Now, at 2 seconds, it would be a different velocity because it is varying on where it is. So the differential of a position versus time is going to be dx dt. Well, what's the difference between dx or delta x, okay, big D versus little d, okay, just means if you're taking these very small changes, we have a dx and a dt. If we're taking the bigger picture, and usually what we're talking about when we talk about this big X, this big delta and big delta, we're talking about a macroscopic change, something that is going to have bigger numbers, not infinitesimally small numbers. So in this case, that would be 2 and 3, our same 2 and 3 that we have there. Okay, so if we are comparing this line right here, okay, with this one, we'll call this trial 1, and we'll call this other one trial 2. What, over the course of 2 seconds, what is the average velocity? What is the average velocity of trial 2? The average velocity. It is going to be 3 over 2. Same idea, right? It's still going to be 1.5. And we can see here in this part, it was going slower than 1.5. And then right about there, it was going 1.5. Then it's going a lot faster. Right there, it's going to be the same. Here it's slower, even, faster, slower. And it's all going to average out to be 1.5 because really, when we go back to this velocity right here, it's going to be the change in position, which again is x final minus x initial divided by t final minus t initial. Those are the deltas there. And if we're taking these spaced out things, all this plus or going slower and faster and slower and faster is going to average out because they end up in the same place at the same time. They end up in the same place at the same time, so the average is going to be the same, okay? So we could have a different one, and we could have something like, well, it still has to be a function that need the vertical line rule, kind of skipped it right there. So we can see here, this would be going faster in the beginning, okay, and then it slows down, and this right here would actually mean it would go backwards, okay, for a time. And so you'd have a negative velocity there, but because it started and ended in the same position over the same time, this average, and this average would be the same velocity, the same average velocity. Does that make sense? Okay. So we are getting, you guys, we are getting close to the end here. Okay. All right. So now, okay, I need another graph here. And all right. So this graph right here, okay, is now not position versus time. Okay, although this is still going to be time in seconds. This is going to be velocity, and the units for this are going to be meters per second. This is going to be meters per second. So if we have 1 here and 2 here, then we're going to have, let's say, 1 second, 2 seconds, 3 seconds, 1, 2, 3, 1, 2, okay? And we have, okay, we're going to have a line like here, okay? Now this happens to be 1.5. Okay, what does this, and let's make it nice. And we're going to say, okay, what does this graph indicate? What does this line indicate? It is moving at 1.5 meters per second. It's moving at 1.5 meters per second the whole time. It is. It's moving 1.5 meters per second. That means it is a constant velocity. It is a constant velocity. Okay? Now, okay. How far did this object go? How far did this object go in the first 2 seconds? How far did it go in the first 2 seconds? It went 3 meters. Okay, now that right there is sort of intuitive, but what I would like to say here is that we're going to use this graph here and to say that this area of this graph is equal to the displacement. So what is 1.5 times 2? So 1.5 times 2 is obviously 3, okay? But this time, velocity times time is equal to displacement, and we will call that delta x, okay? Now, if we were to divide both sides by t, okay, then we have this equation, velocity is equal to the change in position over time, and that's the same equation that we had over here. But now we are manipulating it, really, and this graph right here is the same as this graph, okay? It's the same data, okay, except we've essentially changed it into velocity versus time, okay? And now I'm going to bring it back to velocity times time is equal to displacement. Okay. Now, if we had if we had something like, and I'm going to try to replicate it here. I kind of, let's just say that this was the line, my squiggly line that I had in that previous one. Okay. Oh, where'd it go? I forget where I put that. Okay, but regardless, if we take the area, of this purple, okay, then that area is going to be 3. And you can kind of see here that this hump over here is about the same area as this missing piece right here. Does that make sense? Okay, so now this, in order to calculate the area under the purple, okay, is a little more complicated, and it is something you have not learned in calculus, but you will next quarter, and that is going to be an integral, okay, because next quarter you guys are going to be doing an integral, and that is going to be an anti-differentiation. So if we go back to that previous question where we differentiated it, okay, if we integrate, it's going in the opposite direction. Where did I have that? What did I erase? Okay, so if you take the integral of this, you're going to get this. Okay, but the one thing you don't know is this last number. When you're going in the opposite direction, you would not know what that number is. Okay, and so what you would end up saying is you'd call it some constant. Okay, and you know it would be a constant because only the constant, when you differentiate it, just disappears. Okay, and that is a preview. That is a preview to calculus. So next quarter you're going to kind of just do everything in review. Okay, so one of the key things here before you go, and I kind of lost track of time on your question of the day. Remember that your average speed is your total distance over total time. Total distance over total time. So that means your time, okay, is going to be distance divided by velocity, okay, and your distance is going to be velocity times time, or speed in this case. Okay, and these 3 equations, velocity is equal to distance over time, time is equal to distance divided by speed, and distance is speed times time. Those are the key components in doing the question of the day. Okay, and again, thank you, gentlemen, and thank you guys all out there watching this video, and we will see you guys next time.